Welcome to this explainer. Look, if you're wanting to build a really successful career in embedded systems, there's one core, absolutely non-negotiable skill you've got to master. I am talking about bitwise operators in C. It doesn't matter if you're working with a high-end ARM Cortex-M, an STM32, or just, tinkering around with an Arduino in your garage. Understanding how to manipulate individual bits is the absolute foundation of low-level software development. It's quite literally how we tell the machines what to do.
Okay, let's dive into this. Here's our roadmap. First up, we'll cover the language of hardware. Then, we'll actually meet the bitwise operators. After that, we'll look at controlling hardware with registers, followed by a look at bitwise versus logical operations. And finally, we'll wrap things up by looking at the embedded systems boom.
All right, Section 1, the language of hardware, speaking to machines.
Now, you might be wondering, to truly control physical hardware, we have to strip away all those comfy software abstractions. So how do you actually control it? You might be used to writing high-level code that just says turn on LED or read sensor. But here's the thing, microcontrollers, they don't understand English. They don't even understand C. Deep down at that bare metal level, computers only know two states, off and on, 0 and 1.
Every single integer you type into C is stored internally as a sequence of these bits. It's like a giant puzzle. Decimal 0, that's simply 8 zeros. But a decimal 5, that gets stored as 00000101. Understanding this binary representation is absolutely essential, because the operators we're about to learn, they don't look at the number 5 as a whole concept. They look directly at those specific ones and zeros, and that is what allows us to manipulate them with total surgical precision.
Moving right along to Section 2, meet the bitwise operators. Think of this as your engineer's toolkit.
You can think of these operators as opening up your embedded tool belt, so you can grab, flip, and move bits directly. Let's start with the bitwise AND operator, which is represented by a single ampersand. Now, AND is incredibly strict. It compares two bits, and it requires both input A and input B to be a 1 to actually output a 1. If either one is 0, well, the result is 0. This brilliantly illustrates how we can check or filter specific hardware flags. If you want to know if a specific sensor bit is active, while completely ignoring all the others, the AND operator is exactly what you need.
Next up, we have the bitwise OR operator, using the vertical pipe symbol. OR is much more flexible. It outputs a 1 if at least one of the corresponding bits is a 1. Because of this, it's absolutely perfect for turning on specific hardware components. You could, for instance, enable a single GPIO pin without accidentally turning off the other active components that are sharing that exact same memory space. It's a real lifesaver.
Then we have bitwise XOR, or exclusive OR, which uses the caret symbol. You really want to highlight this rule in your mind. XOR requires the two bits to be strictly different to output a 1. If they're the same, like both zeros or both ones, it outputs a 0. This makes XOR the perfect tool for instantly toggling bits. It's literally just like flipping a light switch. If you need to make an LED blink on and off repeatedly, XOR does all that heavy lifting for you.
Okay, our fourth tool is the bitwise NOT, represented by the tilde. Now, this operator is beautifully simple. It just looks at a sequence and inverts every single bit of its operand. So every 1 becomes a 0, and every 0 becomes a 1. In embedded C, you'll see this heavily used for creating inverse masks. And that's absolutely crucial for safely clearing selected bits in low-level register manipulation, all without touching anything else in the system. Finally, let's look at the shift operators. Left shift moves your bits to the left, which effectively multiplies an unsigned value by 2 for each position you shift it. Right shift moves them right, effectively dividing by 2. It physically slides the data right across the bytes. We use left shift constantly to efficiently create bit masks, like if you need to push a 1 exactly into the 5th position. And we use right shift to decode packed data that's coming in from hardware sensors.
Let's move into Section 3, controlling hardware with registers. This is where we control the bare metal.
So, we're taking things from theory to practice here. A register inside a microcontroller is essentially a physical switchboard. Every single bit is an on-off switch that is hardwired to a real physical component. So how do we flip those switches precisely without breaking the rest of the system? The answer is bit masking. Let's walk through it. Step 1, you create the mask. Say you want to target the 4th bit. You take a binary 1 and left shift it 4 positions. Simple enough. Step 2, you apply the operator. You might use an OR mask to set the bit or an AND with a NOT mask to clear it. Step 3, the hardware reacts. The register updates and instantly a peripheral wakes up, or a motor turns, or an LED turns on. You've isolated your command perfectly.
And I've got to tell you, the sheer scope of hardware controlled this way is massive. We're talking GPIO for general pins, UART for serial communication, SPI and I2C for talking to external sensors, timers for precise delays, and PWM for motor control. Every single one of these relies entirely on manipulating those specific bits inside their respective control registers, the whole shebang.
Next up, Section 4, Bitwise versus Logical Operations. Let's learn how to avoid the danger zone.
I really have to warn you here, because we are entering a major danger zone where beginners frequently introduce nasty, hard-to-find bugs into their firmware. So the crucial point is understanding the fundamental difference between these symbols. Bitwise operators, the single ampersand and single pipe, manipulate the individual bits of integer values. Logical operators, on the other hand, the double ampersand and double pipe, evaluate entire Boolean expressions, returning just a simple true or false. If you accidentally confuse a single ampersand with a double ampersand when you're trying to configure a hardware register, your code will compile just fine, but your hardware will absolutely fail to do what you expect.
Actually, scratch that last point for a second, because here is an even more practical tip that will save you hours of frustrating debugging. The ultimate beginner mistake: using signed integers for bit manipulation. When you write shift a signed integer, the compiler might do something called sign extension. Basically, it drags a bunch of ones across your data and completely ruins your careful bit mask. Always, always, always use unsigned integers when you're shifting bits. Just trust me on this one.
And finally, Section 5, the embedded systems boom.
Let's step back and look at the macro view for a moment. These tiny, low-level bit manipulations, they are the absolute bedrock powering a massive global industry. Now, what's really interesting about this is the staggering scale of the growth. The global embedded systems market is estimated to hit $114.75 billion in 2025. But look at that forecast for 2034. It's projected to nearly double to $212.74 billion. I mean, that's wild. The career potential for engineers who truly understand this low-level C programming is absolutely massive right now.
And that demand, it is exploding across some seriously cutting-edge industries. We're talking electric vehicles, aerospace flight systems, life-saving healthcare ventilators, next-gen robotics, massive industrial automation, and the Internet of Things. Incredible tech giants and huge manufacturing powerhouses are actively relying on engineers with these exact bare metal skills to make their physical hardware come alive. Well, that brings us to the end of our explainer. You now understand the fundamental language of the machines and the core tools you need in your tool belt. So, armed with the power to control physical reality at the bare metal, bit level, what are you going to build next? Grab a microcontroller, fire up your compiler, and let's start shifting some bits.